This is lab 3, where we determine the magnetic field of a bar magnet. So the goal of this experiment is to determine the impact of distance on magnetic field and compare that magnetic field with calculated values to ones that we model in VPython. And the key results is that mu, we got 1.4 ampere meters squared. Calculated off-axis magnetic field was 6.27 e minus 5 Teslas versus the 2.37 e minus 5 from VPython. And as distance decreases, magnetic field increases. So there's three key equations here, which is all part of the same thing, which is the Biot-Savart law, or Biot-Savart law. Note that the first two equations here, the second one you just get by taking the ln of both sides of the first equation, and so this relates, so this is all dealing with the magnetic field of a dipole. Note how the third equation, there's a lot of similarity between that one and the electric field of a dipole when you don't think about when it's specifically on axis or perpendicular to the axis. So the experiment, the most difficult part is just calibrating our phone to determine the point on it where there's a zero force or zero magnetic field, and then from there we're measuring from that point onwards for distance and trying to get the magnetic field at set distances away from the dipole or from the bar magnet. So the key equation in getting the primary results for this part of the experiment is the natural log of the magnetic field equation, where you have ln of k, which is just some constant, plus n times ln of r is the distance vector. And so that equation models the plot that I showed here on the right side, where you have ln of bx versus ln of r. And so the negative 3.3 value there, the value coefficient of x, obviously that's going to be n, as the x-axis is ln of r. And so therefore the negative 15.443 is just ln of k. And so using that you can get k, and we'll do that in a bit here. So as I said before, you take your values from the graph, plug those into the ln of magnetic field of x equation, and you'll end up getting that k is equal to 1.966 e minus 7, and obviously multiply that by 1, and that's the magnetic field of a bar. You plug all of that back into your mu equation, and yeah, to solve for the magnetic dipole moment, and it's 1.4 ampere meters squared. So for creating the model, this is very similar to an electric dipole, so I didn't feel like showing the visualization of what a 3D dipole looks like, but just figure that it's just you're creating a bunch of arrows and placing them with the right direction relative to a certain bar magnet. And then from there you're placing the magnetic field arrows on axis, and then you got your perpendicular axis to the top right. And I just plugged the values that I got from my experiment for perpendicular distance. And from there we end up getting the magnetic field at a 0.45 degrees off of the axis, which I'll show in a bit and discuss compared to the actual result. So here's the result for net magnetic field of that 45-degree point, and just note how the calculated one, which is on the right, is significantly greater than the one that we have on the left. You can see the 7.5 e minus 6 and the 2.25 e minus 5, which is much less than the calculated one. So in this discussion, there's two statements that describe what we observed, which is the second one is that as R decreases, the magnetic field increases. That's a pretty obvious one. And the first one is when you're far away, it's just a zero vector. Again, relates to the second one as distance increases, like distance in the denominator of that equation. For the first what if statement here, obviously the results would have been changed pretty significantly as you go back to that dot product equation for magnetic dipole. Everything changes, both the x and the y component and everything else. It's not great. And for the second what if you stick two identical magnets together end on end, you would expect the results to double in terms of the magnitude. That's just double the length.